Yeah, so my name is Tiago, and I'll talk today about promises and limitations of causality for machine learning interpretability. So to get started with some motivation, we all know that machine learning models are impressive in what they can do these days. Language models were able to solve like this math Olympiads, set a level of gold medal status. Recently, they're also like trying to tackle already open problems in math and sciences. Google was able to use models to try to shave off a few bits in matrix multiplication and actually like deploy that in their clusters. And even in my personal research, I use Gemini to find related work in different areas that you need to do like some logical jump to try to connect those things. But Gemini is able to do those things. I was stuck in a proof the other day, and actually Gemini helped me solve the steps that I was missing. So these models are quite impressive. And given that they're getting ever more present in our lives, I guess everyone here knows that, we should understand how they work. So how does a language model work deep down? And I'll give a quick summary if you're not into language modeling, but basically we start with characters. This is how text is represented on the web. Then we split this per words. Then we have a sequence of words. We initialize the model with a finite vocabulary. These are the words that the model is allowed to know. Each one gets a representation. You look up what each representation here is. You put them side by side. Then you pass this through several layers of the model. Softmax, predict the next item. This is how the models work. Initially, they're randomly initialized, but you train them to predict what the next word is. There's one thing here that is a bit imprecise. I said that they have a finite vocabulary. This is true. But I also said that we split things per words. This is not true. In practice, we have this sequence of characters. We would like to split them per words to get something like this. But because we have a finite vocabulary and words, orthographic words are arguably infinite, or at least they are too many for us to represent explicitly. For rare words, we might not want to represent them like this. In practice, we use something called tokenization, which is a function that tries to preserve most of this word level structure for most words. But for rare words, we split them further into like 2 or 3 chunks. And that's how we represent the text. And the idea here is that we have a finite set of chunks of characters or subwords or tokens that actually represent our text. And then if we plug these tokens here, now we have exactly how language models work. So at a low level, we know exactly how these models work. We know every bit of information that comes in. We know we can inspect every bit going inside of them, and we know exactly what their output is. So is there anything that we need to understand about them if we know everything that's going on? And I guess a lot of people would agree here that yes. At a high level, we really don't understand how these models work. So one question here is how the tokenizer affects the model. So for example, I have this word here that are represented as 2 chunks. What would happen if I had represented this as 1 chunk instead? We don't know. Like the model would change, but we don't know in which way the model would be different. Second thing is how my training data affects my models. So I have trillions of tokens in my training data set. And what would happen if I take one single token that I'm predicting and I'm training my model on, and I change this to another token? Like, we don't know how this would affect our model at a more like mathematical level or at a deeper level. And finally, how the model processes information. We know every single bit of information that goes through the model, but at a higher level, we really don't understand what's going on in there. Like if my sentence has a noun that is singular, how is that information about the number of my noun being used to predict what the verb is, like to make like number agreements? We really don't understand
他
how
据
the
说
process
搞贴
is
了，
higher. Yes. And I think this is these are all very important questions. So like the first one, for example, how the tokenizer affects our model. If we look at the list of famous writers and how their names are tokenized, we can see that writers with non-English sounding last names always have their last names split into multiple tokens, while people who have English sounding last names usually have their names represented as a single token. And if there are systematic differences in how the model processes names based on tokenization, then these differences in tokenization may lead to unfair treatment of different people by the LLMs. So they might make better predictions for certain types of people than for other types of people. If the training data is strong enough to affect our model such that it's memorized verbatim just by being exposed to it once during training, then this memorization may lead to copyright infringements or privacy violations. Like a lot of people use just chatbots to have very intimate conversations these days. And we don't want their information to be leaking just because it was included in model training. And finally, I would say that understanding the inner workings of a model is essential to be able to guarantee that they're safe. Like if we don't understand how the models work, how can we know that they're actually safe for deployment? So I think these are all very important questions, and I'm trying to get a little bit of a glimpse at how we can answer them. And I've done quite a bit of work on tokenization over the last few years, but here I'm going to talk about this thing that I think is quite interesting called tokenization bias. So let's say I'm using one of these chatbots, and I asked it, recommend me a famous writer. How does the model process this? First, we tokenize this thing. We get recommend me a famous writer. And then the model makes a prediction of what the next token should be. Then it samples a token. We take this token, we feed it back into the model. We process it, get the next prediction, and so on, until we have a full sentence. We do this token by token. Then we convert this back into characters, and we have a response. Sure, read Tolstoy. And then the probability of getting as output this sentence, sure, read Tolstoy, is just the product of the probability of generating each of the chunks that that compose my sentence. And this is all nice and good until we notice that Tolstoy is not tokenized as a single token, but it's actually 3 tokens. So to generate this recommendation, read Tolstoy, needs to first generate Tol, then st, and then I. And again, we get the same characters out, and we compute the probability the same ways. But now this probability is the product of 6 tokens instead of 4. And deep down, the characters we're trying to model.
What is the algorithm for this tokenization that makes Tolstoy 3 points?
I'm going to talk about how tokenization is, what the function. I'll talk about that in a bit. Yeah. So basically, deep down, the probability of our data is the same. Like if I look at my training set, what's the probability of the model being exposed to the word Tolstoy? It's independent of what I did to tokenize it, because tokenization is just like a pre-processing step to train our model, but the data is the data. So ideally, we would want this thing to not influence our model too much. But is that true?
The tokenization is based on frequency itself, right? So the fact that Tolstoy is 3 tokens means that it's rare. So it's normal that the machine gives you Tolstoy more rare.
I think there's multiple components to it, but yes, the way tokenizers work is based on frequency. But what we're gonna measure here is what we actually want to answer here is what is the causal effect of including a token on a model's probability of generating it. So we want this causal effect, which means we want to control for things like frequency. We don't want to just see a correlation between tokenization and probabilities, but we want to actually know what is the causal effect of taking this token, removing it from our model. Now this thing is represented as 2 things. How would that change? Or I have this thing that is 2 tokens, and then I include the token for that thing. And how would this change? So this is the question we're interested here. And I can ask like, what is the probability of sure read Tolstoy? But I'm not interested in just that one sentence. I'm interested in the average probability, the marginal probability of generating this word, Tolstoy. And this is the question we're going to try to answer here. In practice, I have these two scenarios here, one where I have the token, the other where I don't have the token. And then I can think about training my model with or without this token in my vocabulary. Then I can measure what's the probability of this word. And then what I want to measure is this difference here. The causal difference, the causal effect of including or not this token on the probability of Tolstoy, or on the probability of whatever the token is, more generally. And this is what I'm calling tokenization bias. And I say this is a bias because the data has a certain probability that doesn't depend on how I tokenized it. So can we measure this? And in practice, I don't want to have to train my model with and without a token for every token that I want to analyze. Training language models is expensive. So can I do this without retraining my model? To answer this, we need to look into how tokenization is actually done. And the most popular algorithm out there is called BPE, by pair encoding. The way it works is we start with some data, and we start with every single possible character in this language in our alphabet. So our strings start at the character level. Then what we do is we take the most frequent bigram and we merge it. And then we get a new representation of our data. And we put this bigram on our vocabulary. And just to keep track of what's going on, I'm going to put this here on an x-axis. Then I take the second most frequent bigram and I add it in. And I do that for k time steps until I have my full vocab. Now I have a vocabulary, and this is where I stop. This is how I generate the vocabulary of my language model, just by iteratively taking the most frequent bigram, one at a time. I take this data set, I use it to train my model, and I have my model now. But one nice thing about BPE is that it's deterministic. So if I have access to my data set, I can inspect what would be the next token if I had changed my vocab size from k to k plus 1. So if hypothetically my vocab size was k plus 1 instead, I would have added this token here in my vocab. And then next, I would have added this token here instead. And these are not tokens because I stopped at k, but they would be if I had k plus 1 or k plus 2 tokens. Now that I have this, what I can do is I can estimate the probability of each of these tokens being generated by my model. So I evaluate this with my model, and then I see that the probability of generating the token is this one. For this one is here, and so on. And I can do that for everything in my vocab, which is nice.
The first is you say we cut off here and then we can hypothetically add, but that's only when we have the training data of the tokenizer.
Yeah, you need to know how the tokenizer was trained.
Here for the probability of being generated by a language model, what is the prefix here?
You take the average across all contexts. So just like marginalize out again. Yeah. Being a bit imprecise here, but yeah, it's the expected probability. You can also take the log to make this a bit nicer. And then you just like do log probabilities. And this is what we actually do in the experiments. But yeah, so here you have like all these probabilities in a line. And then what you would expect had you not like stopped k to be, then you can do the same for the things that are not in your vocab. How do you compute the probability of like underscore hello, given that you don't have a token for that? For some kinds of tokenizers, you need to give this special attention. And then you can check out like this paper where we talk about how to convert probabilities from like subwords into characters and so on. But for BPE, this is pretty simple. You just multiply the probabilities of the tokens together. So the probability of underscore hello is just the probability of underscore times the probability of hello condition done on underscore. So you can get these probabilities here.
But isn't there a large number of possible decompositions into, like here it's only 2 tokens, but
yeah,
it's a longer word?
Yeah, then if you need multiple tokens, but everything like BPE works in such a way that usually these things are
So
just
you're
like
only
two
looking at
tokens.
the cutoff from unigrams to.
Yeah, we're only looking at like this local window here. If you make this window large, then yes, and then you have to multiply 3 tokens or
Because I was thinking of Tolstoy, but that would
Yeah.
be part of the study.
yeah, no. So what you would expect is for this to be roughly a smooth function here. Like there's no reason, like the place where you cut off your vocab, this size k, is completely arbitrary. You just chose it to be like 32,000 because you like that number or because it runs efficiently on a GPU, but there's nothing about the data that made you choose that k. So you would expect on expectation this should be roughly smooth, but what you might observe in practice is that there exists like a cutoff here, and that the probability of the things after the cutoff are significantly lower than the probability before the cutoff, and that the line actually is broken here, and you have this kind of discontinuity. And what regression discontinuity design, this like method from econometrics tells us, is that this identifies the causal effect we want to estimate, at least a local version of this causal effect. So it tells us how the probability of underscore hello would change had I added a token for it, or how the probability of w underscore wo would change had I not had a token for it. So now we have a method to try to estimate this causal effect, and we can do this for language models in practice. So we can train a model where we know how the tokenizer behaves, and then we can put the average log probability of the tokens in the vocabulary here in the order that they were added into BPE. And then the average log probability of the things that are not tokens are here in orange. And then what we get is that the local causal effect is this discontinuity. Here I'm measuring the expected log probability across contexts. So what I get as the causal effect is this 2.88 knots, which is not the most interpretable number, but you can interpret this as an 18 times difference in probability, given that something has a token versus not. So just to make this more concrete, like a word is 18 times more likely under our model if it's represented as a single token versus if it's represented as 2 tokens.
As you train better the LLM, I guess this goes down.
So I didn't put the plots here, but if you, as the model trains, it's actually kind of interesting. Like this tokenization bias, it starts pretty high because at initialization, you basically have uniform distribution. So like that's expected. Then it goes down a lot. And then across training, it actually goes up a bit, which for me is quite unintuitive. I would expect it to just go down with training. If you compare across models of different size, larger models seem to have a smaller tokenization bias than smaller models. So this seems to be mitigated with scale. And this here, I think, was for a 300 million parameters model because we had to train our own models. Like you can do this for any pre-trained model out there if you know how the tokenizer was trained. No one knows how the tokenizer was trained. We asked Elytra AI. Yes, I don't know. We asked like AI2 people. No one knows. So it's a bit complicated to actually like reproduce the tokenizer training exactly, which made us have to retrain these things ourselves.
What's your regression model? Is it constant, or
we tried
linear?
We tried multiple ones. So we tried constant, we tried linear, and we tried gam.
This 18 times comes from
the constant, but it didn't change much.
Estimating the guess, the gap, because you have like these high values to the left, right?
Yeah, but it changed quite not that much. Like it was pretty robust. Should that change? I think also because of the order of like, and then if you also reduce this window here, then it gets a bit more noisy. Like the variance of the estimator really goes up. So you need to set some parameters here to actually get like good estimates. But it's quite robust to how you do the regression. I would say, yeah.
Because I was wondering, so the probability here is the probability of generating those things without conditioning on anything, right? It's just they're like the first token to be generated. Oh,
We actually do it as the expected log probability. We have a data set, and then we take the expected log probability of those characters actually being on that data set. So it's in context.
okay.
Average across all the contexts in our validation set.
Okay.
That's true. So if I understand correctly, here the causal effect is not yet directly related to model. It's more how the segmentation of tokens changed in the data training data.
It's like we have a model trained with this tokenizer, and this model has this was affected by the tokenizer in this way. Like if we had changed the tokenization for this one model, it would have changed the probabilities of the token in this way. So there's like
this one model and data set.
yeah. So like for models, if you choose different vocab sizes. So here is for a tokenizer with 32K. If you use a tokenizer of 8K, then the local effect is different. If you choose it to be 128K, it's also different. So there's like an interaction between like model, architecture, tokenizer, hyperparameters, and so on.
In principle, it could be because there are more outliers to the bottom, right? So if you consider something like a median instead of a mean, it would still be the same.
We did median. We also have like in the paper standard deviations for like instead of taking the expected log likelihood, we also took the standard deviation of the log likelihoods for a token across all contexts. And there's also a big gap. So like these things are not just predicted worse, but they also have a much higher variance. Like the model is more uncertain about how to assign the probabilities. We did 25% quartile as well, or we did median. So like we have those plots in, I don't remember exactly the numbers, but there's also a gap.
Are you going to talk about the mechanism or?
No, we don't know what the mechanism is. We would like to know, but
I'm just wondering if you managed to identify any clear clusters of composite words that have sort of a significantly lower probability. Because I'm wondering, like Tolstoy, for example, you'd expect Tol kind of implies the rest. So maybe that doesn't change the probability so much. But then if you have sort of multiple paths that you can take from that maybe lowers the probability.
yeah, that's interesting. We only took it on the aggregate here for the entire tokenizer. So I don't know. We didn't like do any analysis that is like specific to the kind of tokens. Also, yeah, like my motivating example here is with names of people, but this is for all tokens. So it's like it might be a bit different how things behave. But yeah, it would be interesting to do that kind of analysis, I think. Okay, so I think this is bad news for anyone that has their name from a non-English speaking country. And this is good news for everyone that their name sounds English. My name is very common in Portuguese, and I have 5 tokens. 3 on the last name, Pimentel, and 2 on the first name, Tiago, which is one of the most common first names in Portuguese. So like it's a bit upsetting that even my first name is 2 tokens instead of 1. So yeah, so how do we mitigate this issue? I don't know. One thing that I was thinking about is like, if we can train tokenizers with better compression, we have more things represented as a single word. Like if we take a tokenizer and it like represents things as less tokens, also more things become a single token. So that could be like a nice way to at least mitigate this problem, even if it doesn't disappear. So I try to find tokenizers that compress text better. I guess this is also related to Saibo's research. One thing that I tried was like write up tokenization as an optimization problem and find the optimal tokenizer, but it turns out it's infeasible. It's an NP hard problem. it's not just NP hard, it's APX hard, which means like it's not just hard to find the optimal, but to find anything close to optimal is also hard. We then try to find tokenizers with better compression than the current methods. But what we found is that actually this seems to hurt the models, and we're still trying to figure out why. And we also try to find tokenizers that compress more fairly across languages, but this also seems to hurt the models a bit. So I'm trying to now figure out what this relationship between compression and language model quality is. But this is a bit unrelated to the previous question, just like a side note. Now, any questions about tokenization? I'm gonna move forward.
Are there LLMs where you sort of learn tokenization on the fly? There was some works on that direction.
Yeah, there's like a few recent work that like do tokenizer-free language modeling. So basically, you feed the model like the characters, and then they automatically learn how to chunk it. So there are different strategies on how to do that. I would say that they might still have like some kind of tokenization bias because you still need to set some kind of threshold to where when something stays as one chunk versus as two. And I think a lot of like this effect is also, it's related to frequency or the probability of the things. But if your corpus is dominated by English text, I think your other languages are always going to be in a disadvantage. And I think that's also true for this tokenizer-free models, although I haven't checked. But I'm pretty sure they are also going to have like a problem that is similar to this. Just need to operationalize things slightly different.
So I think it's a very interesting thing that you see that cutoff of 2.88 nats.
Yeah.
But the thing is that, like for example, I think have you tried using people's name that are roughly the same level of fame, like 20th century like physicists? Some of them are German, some of them are American. Like, have you tried like how often they are generated?
Yeah, no, I haven't checked that. Like literally, I use that more as a motivating thing here. But I think it would be interesting. Like there are also like a lot of methods from econometrics to try to do this kind of thing in different ways. And here we used regression discontinuity design because I think it's kind of neat and it fits well to how BPU works. But there are methods that try to control for like
because you need to
other factors.
Footing.
Exactly. So there are other methods that would try to approach it in the way that you said, like you try to get some features of the words, and then you try to do some kind of control between your control and your treated sets. But I didn't try to apply them. I'm not as familiar with them yet because I never use it. But it would be interesting as well. I just think that this is a very neat method, although it's quite limited in some senses.
I can't help thinking about the mechanism. And I'm wondering whether it's something very simple, such as if you have more tokens, you have more chances to make a mistake.
Yeah, I was thinking about like, let's say your model just like is a smoothed version of the correct distribution, you would also see some effect like this. But I think it's quite weird, like this trend that you actually like reduce a lot the bias and then it kind of increases across training. So that makes me think that maybe the mechanism is slightly different. I don't know what exactly the mechanism is. I have no idea.
But I think this is I love this approach of taking these kind of econometrics methods.
Mm-hmm.
A lot in that field is about mediation analysis and so on. So I wonder whether there might be good tools there to actually home in on the mechanism.
Yeah, so like the first author on this paper is Pietro Lasci, and he was an economist by undergrad and master's. So we joined forces to do this kind of analysis. The second part is also about using econometrics to analyze language models. So now moving on to the effect of training data and how it affects the model. Like basically how I think about this is a lot about like how models generalize and how models memorize the exact training data that you have. And in here, I'm going to talk specifically about memorization. So let's say you have like a very large corpus with billions or trillions of sentences and tokens, and one of them is this one here. The story so far. In the beginning, the universe was created. This has made a lot of people very angry and been widely regarded as a bad move. This is a quote from The Hitchhiker's Guide to the Galaxy. You use it to train your model, you tokenize it, you train your model to be able to predict this. Let's say this is like only one instance of your training set. Then I go use the model, I give it like this prefix here, tokenize it, and then I ask the model to generate a continuation. And let's say it generates exactly this continuation, like token by token, it generates exactly what this sentence was. A lot of previous work has shown that depending on the frequency of a document or some text in your training set or so on, this actually happens in the language models. Like they are able to generate token by token exact reproductions of what the training set was. And this is actually like the topic of a lawsuit from OpenAI, from New York Times against OpenAI. But in those analyses, they usually don't control for like what is the causal effect of like training on this thing. It's more like this thing is on our training set. Can the model generate this verbatim? And we wanted to get a deeper understanding of what is exactly going on here. So we tried to ask this question, like what is the causal effect of including an instance in training on the model's probability of generating it? So very similar to what we did in the last part of the talk, but now here talking about memorization. You train on this one specific instance. How does the probability of this same instance changes when you're doing like inference? So again, to make this more concrete, I train my model with this instance or without this instance. Then I get the probability of this instance under my model. What is the difference? This is what I'm calling memorization. It's the causal effect of training on the probability that the model assigns to the same example. In practice, again, don't want to train and retrain my model several times, very costly. So how can I estimate this? And again, let's try to think about like what this thing is that we're trying to measure. So basically I have here the performance on a training batch, the expected probability of my training batch, given that I trained on it. And then I have the performance on this training batch if I had not trained on it. And this difference is what I'm calling memorization. So memorization is the difference between like performance with checkmark versus performance with X. And the problem here is that I did train on this batch. So I cannot measure this thing that is a bit like whatever the word in English is for when you can't see it well. The thing with the X mark, I can't measure this. So how do I try to measure this difference? This thing with the X mark could be here, or here, or here. We can't know for sure where it would be without retraining it. But what we can do is we can try to look at other data to try to get an idea of what it is. So for example, I have access to a validation set, and I can measure what the performance on the validation set is. And I know that I didn't train on my validation set. At least I hope people didn't train on the validation set. And then I can make assumptions about how these things relate to try to measure memorization using the validation set. One assumption I could use is that these things are identically distributed. If this is true, then these two things should match on expectation. Like I'm sampling my validation set. If it's identically distributed to my training set, if I had not trained on my training set, it should behave the same as the validation set, at least on expectation. But in practice, this might not be true because usually when you're doing like large language model training these days, the validation set might be from a different set of data as your training set, or it might be a bit more clean or so on. So like this identically distributed assumption might be too much. Another assumption that you can use is this parallel trends assumption. What it says is, you can go back to your model before you trained on this checkpoint and see what was the probability that your model assigned to both your training batch and your validation set at that time step. So before you trained on it. And then the assumption here is that if you had not trained on this batch, it would have improved at the same rate as the validation set. So this is a weaker assumption than the IID one. It's still an assumption, but basically you're saying that this diff here is the same as this diff here. Now, if you have this assumption in place, you can measure memorization by basically doing some like algebra here, and as this difference in differences. And this is another method from like this econometrics literature to try to estimate causal effects. We do this for Pythia, the 7B model, and we get this plot here. What is in this plot? I have all my batches that my model has seen across training, or I have like every 1,000 of them in there. And then I have all the checkpoints that were saved across training as well. And then each square here, each dot in this plot, is how much that batch is memorized by that specific checkpoint. So I can see how memorization changes across training. And this is what one row represents. It's like for one batch, how much memorization of this batch changes as I train on it. And this, we just visualize this row here on this bottom plot with the y-axis being memorization.
Do you need to worry about a given prompt entering many times in your data set?
Can you repeat?
Do you worry about the fact that given what your batch of text you're studying could enter many times in your data set?
So for here, we use the deduped models version of this Pythia models. So they guarantee, like they went into the training set and they removed any duplications. If you have duplications, you have to worry about this. Like in theory, this method does not work if you have duplicated data. So that's one limitation. We're actually thinking about how to expand this. Like basically the name of this method is differences in differences. And people in econometrics have talked about how to change this method such that if you have like, if you're talking about like people taking drugs or pharmacy medicine, and they take one dose versus 2 versus 3, how to represent this using these methods. So we're trying to think about how to expand the work, but in here it's only once, yeah. But one interesting thing about this plot, in my opinion, is first, that before you train on this checkpoint, the value is always 0. And this is a nice sanity check. Basically, before you train on this batch, it seems that the parallel trends assumption holds, like the difference between the training set and the validation set is always 0. Right after you train on this batch, you see this peak of instantaneous memorization there. Then you see that it goes down a bit and it asymptotes at a certain level. So what seems to be going on is like there is some partial forgetting of that batch after you train on it, but there's something that is like persistent about like the memorization of this thing, and that persistent up until the end of training. And it never goes back to 0. If we look at the different batches across training, we see that batches later in training seem to have more persistent memorization than batches earlier in training. And then we can also see how this instantaneous memorization behaves for models of different sizes. So in this small plot there, in pink at the top is the memorization for a 12B model. And as red on the bottom is the memorization for a tiny 70 million parameters model. So you see that the larger the model is, the stronger the memorization is, at least for this Pythia family. So
sorry, but the x-axis, how does it align with the other?
Basically, we just have the diagonal, and then like it's just the checkpoint. So it's basically this diagonal here put on a line.
So what's that I didn't understand that top plot.
This or this?
The other one, yeah.
These are all the batches that you use for training, and these are all your checkpoints. So like at training step 110, how much the model has memorized the first batch of training, the second or the third one. Yeah. And then this diagonal here is what I'm calling instantaneous memorization. So right after you train on something, how big is this peak here?
Oh, I see. So you're taking that size of the peak and you're sweeping over.
Yeah. So, and then this is basically just the peaks. Yeah. And what you see is that like the larger models have much higher peaks than the smaller models. This is also true for other statistics, like the final memorization is also larger for the larger models than the smaller ones. And yeah,
This is over a single epoch.
this is single epoch training, but the way PyTia models work is at this like dashed line here. Actually, they didn't have enough training data to actually do a single epoch, so like they start repeating. So this part here is repeated data, but up to here it's a single epoch. Yeah. In theory, it was supposed to be a single epoch, but because they wanted to keep the hyperparameters the same for the deduped models and the duplicated models, and because they removed data, they had to do like a partial second epoch. Yeah.
So I'm not for the error
It's across the data. Like you basically have like this is the expected memorization for a batch. So you have like all the single points of that batch, and then you can get error bars.
I'm a bit confused. Your test set, you would need to have, you look at the small beginning of a given paragraph that also is also present in your test set.
Like you take the difference between the probability that your model assigns to things on the training set versus what it assigns to the validation set. So like you have your validation set that is never trained on, and you have your trained set that you're trained on at some point. And then you can check what their difference is.
But when you do this, is it conditioned? I mean, do you condition to specific data in your training set and your test set, like those that start with some given?
This is like the expected memorization for an entire batch. So like in this batch, you take the average across all sentences on it. And then you also have like the expectation on the validation set. And that's how you get your diffs. And then you just take the diff of diff. So like this is not measuring like, okay, so one thing is like I said that I wanted to measure this like this difference at the instance level. I actually put an expectation here, and I do that for an entire batch. Yeah, because it's hard to identify like things for a single instance. So yeah, you're right. Okay. So many animations. Okay. So like I think like one important takeaway from this is that larger models seem to present stronger memorization than smaller models. And what this means is that this is not a problem that's going to go away with scale. It's actually getting worse with scale. So we need to think about memorization like it's a problem that is not going to solve itself. So we need to think carefully about this. Any questions about memorization or?
Apertus has this special loss that tries to prevent memorization. Did you run this by chance on Apertus?
They do the fish loss, right? Like the golden fish loss. So I didn't run this on Apertus. I should talk to Emmanuel or to Antoine about it. But like it prevents this verbatim memorization, which is the way like a lot of people think about memorization. Basically, if you sample from the model, if this is going to be what you're going to sample with greedy decoding, like if that sentence. But if you're thinking about just like the probability your model assigns to the entire sentence, I think that would affect it much less. Because what happens is just like, okay, so for one of the tokens, you don't generate it, and then you deviate from that sentence on average. But like the entire probability of the sentence, I think it will still be pretty memorized. So I guess like how you define performance or how you define the thing that you want to take your causal effect on is quite important. And it depends on like what your concern is. If you're concerned about just like verbatim memorization, then like using this with like another metric, it's pretty easy to change what is being estimated here for the causal effect. Yeah. And now, like, as the last part of the talk is about how models use input information. During my PhD, I was working a lot with probing. At some point, I started thinking about like causal effects on the models. And more recently, I got very interested in this notion of causal abstraction that is like pretty prevalent this day in mechanistic interpretability. Maybe I shouldn't say prevalent. It's the best framework out there for mechanistic interpretability, but not a lot of people use it, I guess. So this is what I'm going to talk about now, this notion of causal abstraction. So the goal of mechanistic interpretability is to achieve this causal understanding of how a model makes decisions. So basically, we want to understand how a neural network encodes information and how this information is used by this network. How do I do this? One way to do this is with this idea of causal abstraction. So for causal abstraction, you start with a neural network that is already trained, fixed, and then you propose an algorithm that you think the neural network is using to solve this task. And then what you want to do is you're giving these two objects, and you want to find if there's an equivalence between them. So you want to see if they are equivalent in a certain sense. If they are, you say that the neural network implements this algorithm. How do you do this? Basically, you take your neural network and your algorithm, feed it an input, propagate it, see if the outputs are the same. So this is the basic sanity check. But for causal abstraction, it's not enough that these things behave the same under normal inputs, but you also want to see if they behave the same under interventions. And the way you do this is you try to see if for every node in your algorithm, there exists a neuron in your neural network such that under intervention, they behave the same. What do I mean by intervention? You create a copy of your neural network, feed another input to it, propagate it, and then for this neuron and this node, you transfer the information from this copy back to the original run, change what its value is. This is what is called like an exchange intervention, and then you propagate. And then you see if the outputs are still the same. If this is the same under every possible intervention that you can do on your model, then you say that these two things are equivalent and that you have a causal abstraction here. And this is all nice and good, but what I said is for every node in your algorithm, you want to find a neuron in your neural network that encodes this information and that is equivalent to it under interventions. What this means implicitly is that this method is assuming this thing that you can call the privilege basis hypothesis. Basically, it assumes that the neurons in a neural network form a special basis where these higher level concepts are encoded. So like the grammatical number of an object, or whether the object flies or not, is going to encode it in one neuron versus another. What a lot of people in interpretability believe, though, is on this linear representation hypothesis, which means that concept information is not encoded in the neurons, but actually on linear subspaces of the model. So there exists like some kind of rotation of your hidden space such that the number of your words is encoded on some kind of like direction in representation space, but not on the neurons directly. Can you change causal abstraction to consider this? And the answer is yes. This was done before by Atticus Geiger and colleagues. The way you do this is you take your neural network, you split it into two, and these things here represent the same neuron. Then what you do is you add a rotation matrix here that basically exposes your latent variables. So you have your neurons, you just rotate them such that in your latent space, these things are concept aligned. And then you see if you can find out whether a node in your algorithm is equivalent to the latent variables, this exposed latent variables here under interventions. Then you undo this rotation, which you can do easily, place it back on your network, and you see if under interventions these things still behave the same. If they have the same outputs under every intervention, nice. This is a linear abstraction. So your algorithm linearly abstracts your model, basically. We can go further than this, though. Like, we're assuming here the linear representation hypothesis. But we know that some information is encoded non-linearly in neural networks. So for example, days of the week seem to be encoded in a circle in the representation space, or numbers in some kind of helix in embedding space. And the linear representation hypothesis cannot model those things. So what can we do? We can try to assume some kind of nonlinear representation hypothesis to try to model those kinds of non-linearly encoded information. There's no reason why we need to restrict ourselves to linearity if we're talking about deep neural networks, and the whole point is that they are non-linear. So can we change this to consider non-linearly encoded latent features? And the answer is yes. This is quite simple to do. We just change this rotation matrix here to consider any nonlinear bijective function that will expose this nonlinear latent features. And then we see, again, if these latent variables are equivalent to the node on your algorithm. And basically, you're just like exposing these latent variables here with some kind of nonlinear bijection function. At this point, well, and then if they have the same outputs, again, then this is a distributed abstraction. The problem here is that actually this doesn't work in theory. Like, if you allow for any bijective function to be exposing your latent variables, what you can find is that any algorithm will be a distributed causal abstraction of any neural network. So what this is saying is basically like, up to using rotations for your causal abstraction, the method works nice and good. But if you want to find nonlinear representations on your network, you have to be more careful, because your probe, this nonlinear bijection function, can actually learn how to match the algorithm for you. This is also a problem in practice. Like, if we take, for example, a PyTia model of different sizes, and we see if it can perform an indirect object identification task, we see that the large models perform well on this task, and smaller models cannot do this task. If we use just a rotation matrix to try to expose the latent variables of our model, we find that the trends kind of follow the model. So when the model can't perform the task, you can't find the algorithm. When the model performs the task, the method can find the algorithm. If you use nonlinear functions, even when you have like a randomly initialized model or small models that cannot perform the task, your method can always find some kind of like bijective function that exposes and that makes the model pretend like it's performing the task. So basically, the conclusion here is that these causal interventions are not enough to avoid finding spurious explanations for your model. I think a lot of people in MacInterp think that if you do interventions on your model, you're safe, because if you can control your model, it means that you understand how it works and that this is like a true mechanism. But actually, you can find any mechanism you want if you just like look hard enough in your neural network. And then the other question here that this opens is like, how can we reliably search for nonlinear features in our models? Like, up to this linear representation hypothesis, we were safe. But if we want to use like arbitrary bijections to try to find features in our model, we get that those transformations are too powerful. So how can we try to search in a nice way for this helix structures or for the circular structures in our model if we can't make our probes stronger without finding spurious things? And this is the last slide of the talk. So to conclude, I think that causality offers a very principled way to do machine learning interpretability. You can estimate tokenization bias and memorization with it. and you can find different effects using this methods. But you should always be careful when interpreting these results to derive actionable items. Like there are like specific assumptions that the methods use, or there are mainly the assumptions that your methods use that might not allow you to like indiscriminately just like think that increasing your vocab size will always help because you have tokenization bias. Beyond that, causality lets us operationalize mechanistic interpretability, but it's not sufficient to avoid the spurious interpretations of a model. So we need to be careful, even if we're using a causal method, to not overclaim what we're finding. That's it. Thanks.